Hello, hello, hello.
Hello Prajwal, can you hear me? Prajwal, did you hear me?
Guys, just to let you know, this lecture will start at 6:30. I just put 6 o'clock because I didn't want people to walk in when he started talking. Make sense? He's way too cool to watch you guys walk in and disturb his talk. Hello? Live stream is very delayed. The live stream is very delayed. Everybody needs to. Uh, I think
See, before,
Wait,
now this is not
wait,
sharing.
wait.
Before it was sharing. And
Where
you
is
went there and
अच्छा,
changed.
it's still there.
And you changed it. You have to change it
विजन
again.
जाके उनको बोलना कि ये वाला स्क्रीन शेयर करना 10 मिनट के लिए ये
The
इस
screen on
वाला
the
screen. Which line professor choose for the case study?
भाई क्या है ये?
Rupa, when the professor says they're coming.
I'm happy I'm going. नाम था ना?
Wait, है उस वीडियो का नाम बता.
बता ना?
नहीं हाँ पता है सिर्फ यही दिखाना है.
बोलना हुए. There.
The incredible science of CERN.
Why choose when you can have it all? By joining Albert School International Bachelor's in Business Administration, you will learn how to leverage AI, data, and maths for business purposes. This is a 3-year highly selective program in partnership.
Hello. Hello.
About being one cool thing about being a mildly successful
Tell him to.
YouTuber is that occasionally I get an invite to a cool place. And earlier this year, I got an invite to go visit CERN, which when I saw, I was like, hell yeah. So I booked a quick flight over to Geneva and had a visit. On the day, I went and saw one of the detectors. I went and saw the control center, the data center, and also the magnet factory. So let me show you what I saw. At CERN, there's lots of names for lots of different things. I'll start with a bird's eye view just to orient you. This is CERN, a campus of buildings and load of tunnels underground at the border of Switzerland and France. There are many different loops for accelerating particles, but the most famous and biggest is the Large Hadron Collider, the LHC, which is a large ring with 2 proton beams circulating inside in opposite directions. It's got 4 big detectors on it, which are placed over crossing points of the proton streams. When the proton streams cross, protons collide and energy is turned into matter, making massive particles, which then decay into a stream of other subatomic particles. These detectors are made of many panels of gas that detect when a particle passes through them, as well as loads of electronics and magnets. The point of them is to track every single particle that comes out of a collision. I went down and saw one of the detectors, the Atlas detector, which was used to discover the Higgs boson, along with another detector called CMS. There are other detectors too. Alice, which looks at what happens when you collide lead atoms into each other. Yep, you can lob lead atoms around the Large Hadron Collider too. When lead collides, it forms a crazy dense and hot form of matter called a quark-gluon plasma. Quarks and gluons are just other kinds of particles. And the other detector is called LHCb and looks at some other particles called beauty particles. The Atlas detector was absolutely awesome to see in person. The Higgs boson discovery is such a big deal in the history of physics, so I felt really fortunate to have gotten a chance to see the detector up close for myself. And the thing that impressed me was not only the sheer size of it, and it was huge, but also the density of everything. You know, there's loads of big things in the world like buildings, but not many building-sized things that are made of solid technology. There was electronics, detection panels, pipes, wires, giant magnets, and all of that stuff has to work together flawlessly. They can't have a single gap or a section that isn't working because they need to be able to account for every single decay product of a proton-proton collision. So it was a marvel of engineering to behold, massive and densely intricate. And one cool thing was the giant hole in the roof, which is where they lower down all of the bits of the detector. The second place I visited was the control center, where there were 4 big circles of computers and monitors, and loads of monitors with all the information about the status of all the different bits of the LHC. It was really quiet when I got here because they're not currently running experiments. Right now they're working on upgrading the luminosity of the beams, which means more collisions per second. With the luminosity upgrade, they're aiming to get 5 times the rate of collisions and 10 times the amount of recorded data. The goal is to get more statistics on the Higgs boson. They've done the bit where they discovered it, but now they really want to study it. You see, when you create a Higgs boson, there are a number of different particles it can decay into. By measuring the probabilities of it decaying in these different ways, scientists can test to see if the standard model, our fundamental description of particle physics, is actually correct. Any deviation from what the standard model predicts would be very interesting. And it's kind of funny, the standard model of particle physics is this incredibly good
Could everybody please get up and move to those 2 columns of the LHC? Because those are ones that are going to be visible through the camera that Mike sir is going to be looking at. So I'd appreciate if everybody here could get up. Yeah. What? Uh-huh. Oh. Oh. Sorry. Ask him to switch it. आश्रय मैं हाँ मुझे दिखाने को बोलो ओ I'm unmuted. I left the meeting. I left the meeting. वो वहाँ जाके कर लेना जाके कर लेना hello Mike, can you hear me sir?
I can hear you.
All right, so I think everything is working right now. We could just go through a checklist once. uh, could you turn on your video once, sir?
Okay, video on.
Yeah, so we can see you. And how well can you hear me right now?
That's good.
All right, cool. So we have everybody sitting, as you can see in the video, we have everybody sitting there and ready to listen to you. So I think I'll get on the quick introduction and then we can go on with your presentation if that works.
That works.
All right.
Do you want to start? You want to start at 3 o'clock or? Sorry, whatever.
We can wait for 10 more minutes if we don't mind.
Okay, no problems, of course.
Cool. Sumit. Sumit. Huh. All right. Sir, shall we begin?
Okay, ready when you are.
Okay, I'll give a quick introduction about you to the audience sitting here, and then I think we can go ahead with your presentation. So, good morning, everyone. Afternoon, actually. It is my distinct honor to introduce to you our special guest today, Dr. Mike Lamont. He is the first guest lecturer of the Cosmic Voyage annual series that we have, our uh, weekly event. Now, he's currently the director of accelerators and technology at CERN, which is a European organization for nuclear research. He now oversees the development, construction, and operation of advanced particle accelerators, and basically at the forefront of technological innovation and at the enables any new discoveries in particle physics pretty much. So he first began his journey with CERN in 1989 when he joined as a fellow and starting his remarkable career as a researcher at CERN. Now, he earned his PhD from the University of Liverpool in 1986, and his journey at CERN is actually inspiring. He started as the engineer in charge for the SPS and LEP in 1991, where the SPS is a super proton synchrotron and LEP is the large electron positron collider, which were at the time state of the art facilities. Like it was present absolutely nowhere else in the world, and he was at the forefront of it. Later became the LEP mission machine coordinator, and then he became the deputy project leader for the LHC, and later the LHC machine coordinator. LHC being the Large Hadron Collider, and he was there when its initial operation started in 2008. Now, he was also the leader of accelerator operations from 2009 to 2016, where he led the beam-based operations of CERN's accelerator complex. And then in 2017 onwards, he was the deputy head of the beams department, where he coordinated the physics behind beyond collider study and represented CERN basically on many international scientific advisory committees. Ever since January 2021, he's been at the position he's in right now, the director of accelerators and technology. So basically, we're very privileged to have him speak for us, and honestly, it's an honor to have you here, sir. All of us are excited to hear from you. And just before we continue, I'd like to show you something special. I'm not sure which screen is visible right now, but we all were wearing T-shirts which has the Large Hadron Collider printed on the back of it. Which screen is visible right now, Sumit? Us or me? This guys. Can somebody from PAC stand up and show the T-shirt? Turn around, show T-shirt. Here, get up. Whoever has a PAC T-shirt, get up and turn around, please.
Very nice.
I don't know if you can see it, but yeah.
Yeah, no, I can see these people. Thank you very much.
With that, please join me in inviting Dr. Mike Lamont to begin his presentation. Also, just one quick question before we begin. Are you open to questions at the end of the presentation, or do we not have the time?
Yes, certainly. I mean, on time, just come in if I'm going on too long. I'll aim to try and finish the presentation in about 3/4 of an hour, and then time for a few questions.
All right, sounds good to us. Thank you so much, sir. I think we can begin. Guys, big round of applause, please.
Okay. So many thanks for the very kind introduction. It was a kind of broad brief on what you wanted to hear about, so CERN and how it all works. So I pulled together some of the key threads which are keeping us busy at the moment, and I'm going to try and give you some sense of what's going on at CERN at the moment and some sense of how it all works. So our goal is to understand the most fundamental particles and the laws of the universe. So this is our mission. We are the European Laboratory for Particle Physics. We have submissions, but that really is what we're here for. We get some of the brightest minds of the world in to help us out with solving some of our problems. This is John Ellis, a theoretical physics, now retired. This is Fabiola, our present DG. So this photo is from the 4th of July 2012, which is Higgs Day. So this was the, at this point she was spokesperson of the Atlas collaboration. And here you see the scene in our main auditorium where the announcement of the Higgs discovery was made. So this was, this, and this here you see illustrated the true goal of the ultimate prize of experimental physicists. This is free t-shirts, a drink after that event. And of course, this led to the final piece of the standard model. I'm not too sure how familiar you are with this, but you have the quarks, the leptons, neutrinos, the gauge bosons, and holding it all together, the Higgs boson. Monumentally successful theory. We know it's not the full answer to everything, but it's proving remarkably effective at the moment. So unreasonably effective is the term you'll hear used. Huge amount of effort gone into trying to find discrepancies to it, but nothing's showing up for the moment at the LHC, despite having discovered the Higgs boson. So who is the Higgs? Why did he freeze in the universe? Why do we exist? Who is dark matter? Who saved us from complete annihilation? Some big questions still to be answered. And if we peer out into the universe, this is a photo from one of the first deep fields from James Webb, we can see that it's actually a cosmic web of dark matter decorated by stars. So this is the large-scale structure of the universe. And what we know is, the message here is, don't let the bright lights fool you. The dark side controls the universe. Dark matter holds it together, and dark energy determines its destiny. So you see the kind of makeup of the universe in terms of ordinary matter that we see as stars. There's a lot of gas and other stuff out there as well, but dominated by dark matter and dark energy. So big unanswered questions. So coming back now to CERN, just a couple of intro slides. So we were founded in 1954 in the aftermath of the Second World War, 12 European member states, now up to 24, with 10 associate member states, of which India is one. And a lot of cooperation agreements with countries around the world. About 2,600 staff, 1,000 graduates, and a lot of associates, users. So these are the experimentalists who come here for a year, a lifetime, or a week. And really a laboratory for people around the world. So these are the users by country of their home institutes. So you see the member states, you see the associate member states, India, America playing big role, over 2,000 users there, so playing a big part in some of the major experiments, and a lot of people coming in through the cooperation agreements. So a big international family. Not very exciting, but just to show you the organogram for the organization, I just want to highlight two kingdoms over here: research and computing. So this includes the experimental physicists. So this is the detectors. And over here we have accelerators and technology, which I'll go into a little bit more detail. But these are where I would like to say the real work is done. But of course, we need all the other components to make up a fully functioning organization. But this is where I'm going to spend most of my time, in the accelerator and technology sector. So this is the organogram. So we operate, maintain, consolidate, and upgrade the accelerator complex and associated technical infrastructure. So all the power, cooling, and ventilation. I don't want to go into this in any detail, but just to you can see the different groups covering the different specialities that have to be mastered to run the complex. So cryogenics, machine protection, magnets, vacuum, radio frequency, power converters, beam instrumentation, etc. Engineering, the big electrical network, transport, cooling and ventilation groups that look after the whole infrastructure for the whole site, controls, etc. And you see compartmentalization and a level of specialization. So we're about, in this sector, we're about 1,300 staff, around 1,000 fellows, graduates and associates. But we are operating the facilities which are used by around 12,000 scientists from around the world that you saw in the previous slide. So our responsibility, exploitation of the accelerator complex. I'll come back to that in a little bit more detail very soon. We're looking for an upgrade of the LHC to the high luminosity LHC, the HL-LHC. So you see us, this is a mock, this is real magnets in something called the string, where we're testing out the magnets for the high luminosity LHC on the surface before they go underground. We're looking at future options. We'll come back to that. And really importantly, you saw this in the group structure, all the technology, the engineering, and the research and development for all the components which go into the accelerators and experimental facilities. So accelerators are us. So this is a complex. We've got a LINAC, which is going to produce H- ions. We're going to inject those into the booster. We'll strip off the electrons on the way in, and the protons go off to facilities around the complex. So we put protons onto target to produce radioactive ion beams, radioactive isotopes in Isolde. Put protons onto target to produce neutrons. So a neutron timer flight facility to two experimental areas over there. Protons onto target to produce antiprotons, which are trapped, cooled, and go in the AD, Eleanor, and then off to experiments doing antiproton physics. We've got protons onto targets to produce secondary beams of hadrons and leptons over in the east area, and higher energy protons onto targets to produce a wide variety of beams, including a muon beam over in the north area. So these facilities, thousands of physicists besides those working on the LHC, so rich physics program. This is our proton chain very briefly. So you saw LINAC, the source, LINAC 4, booster, PS, SPS, LHC. And you see the LINAC is 86 meters long, booster 160 meters in circumference, PS 600, SPS 7 kilometers, and the LHC 27 kilometers. So pumping up the jam, producing higher and higher energies as we go through the complex. And you see each of these machines serving various facilities with lower energy protons than those actually realized at the LHC. And I'll just, and that's the kind of graphic, and that's the kind of plan of what it looks like. So LINAC 4 transfer line into the booster, around the booster, off into the PS, and then off into towards the SPS. So just going to very quickly run through those just to give you a little bit a more better view of that, because it's sort of very conceptual like that. But LINAC 4, you see part of LINAC 4, H- ion source, 95 keV. The LINAC accelerates the beam up to 160 MeV and shoots 80 microseconds of beam out every 1.2 seconds. And you see the components, RFQ, drift tube LINAC, etc., coming down the line, accelerating the beam up to 106 MeV, and you see the RF frequency being used there. The booster from the 70s, a really old machine, 4 superimposed rings, 157 meters in circumference, and this takes the protons from 160 MeV up to 2 GeV, and this is cycling typically at 1.2 seconds. So beam comes in, accelerated, and out in around 530 milliseconds. And we actually strip off the electrons from the H- with a stripping foil at the entry point to the booster, allowing us to over-inject beam into circulating protons. So we do multi-turn injection using, and this is called charge exchange injection, and this allows us to get very nice small proton beams in the booster. And just for real, that's what it looks like out in the field. So this is the booster here. This is the H minus coming in from the LINAC. It goes in here, 530 milliseconds, an extraction out, and then off down towards the PS. And you see here, we got 4 rings. So you see the H minus, the beam pipe splitting into 4 here. In fact, that's what it looks like from the other side. And you see photos like that and you wonder how it can ever work, but it does very well. PS, 66 years old this year, built in 1959, 628 meters in circumference. And this takes the protons from 2 GeV to a maximum of 26 GeV. And we're going fast cycling between 1.2 and 3.6 seconds. So beam in, accelerated, and out in seconds. And we do some, just show you, so LHC wants 72 bunches from the PS via the SPS. So we take 6 bunches from the booster, we accelerate, we split the bunches longitudinally, and then double split them again. And here you see 4 bunches from the booster, another 2 to give 6. We accelerate, and then we do a triple splitting, and then 2 double splittings to give 72 bunches of the right intensity, goes off to the SPS and then off to the LHC. So some really quite sophisticated RF radio frequency manipulations involved in doing that. The SPS, getting a bit more serious now, 6.9 kilometers in circumference, warm magnets at 2 Tesla, takes the beam up to 450 GeV, deals with high intensities, and sends a maximum of 288 bunches to the LHC. And when the LHC is happily colliding its beams, it sends beam to the north area and a material testing facility called High RadMat, and a plasma wake field acceleration test facility using protons as a drive beam at a wake. And so physics being done by a broad range of physicists out in Eleanor, antiprotons, radioisotopes, a wide variety of stuff going on in the east area, neutrons, and again, wide variety of stuff out in the north area. Going to the LHC, 27 kilometers, 1,232 main dipoles, which are 14.3 meter long, 858 superconducting main quadrupoles, a lot of corrector magnets. Main magnets are using niobium titanium superconductor cooled at 1.9 K. So a huge cryogenic system, 150 tons of liquid helium in the system, around 90 tons of that at 1.9 K. And just to give you an idea, 12,000 amps in the dipoles gives a field of 8.3 Tesla, which enables us to bend 6.8 TeV protons around the ring. Actually, that would give you 7 TeV, but for various reasons we haven't got there. Okay, so that's an overview of the accelerator complex. I don't want to spend too much time on the technology, but innovative accelerator technology underpins the physics reach of high energy and high intensity colliders, a powerful driver for many accelerator-based fields of science and industry. And I've been at CERN now for 35 years, and this has been a revolutionary progress across the board on all of these. We could not have done, I started on LEP, we could not do the LHC with the technology we had back then, and the push that CERN has been part of has enabled us to take the LHC up to its very high levels of performance. particularly as a superconducting machine. So technologies, high field magnets, high temperature superconductors, high gradient accelerating structures, challenging high technical domain, so large scale mass production to one-offs, very high performance, precision engineering, precision metrology, material quality, controls is exquisitely challenging, it's a harsh environment. We need high reliability and availability. It'd be nice if it was affordable. We want to use low CO2, so we're taking this seriously these days, and we engage industry wherever possible. And we do come to the associate member states, so India called upon where their expertise matches what we need. I'll just show you the list of some of the things we look for. So not only is it high tech, but it's some of it's low tech. So you saw the PS, still the same magnets in there. They've taken a bit of looking after, but they date from 1955. So that's one end of the scale. And this is, I'll come back to high luminosity LHC later, but this is an niobium-3 tin quadrupole, a prototype that worked well under test in one of our magnet test facilities. And just to flash some of the R&D we're doing: high field magnets, low temperature superconductor, high temperature superconductor, plasma wake field acceleration, warm 12 gigahertz radio accelerating structures, and also superconducting RF. So looking for increased performance, so higher fields and more efficient, higher quality RF cavities. Right, coming back to the LHC, big, cold, high energy, lots of kit. As I said, I've done these numbers, 400 megajoules stored beam energy. So this is a fully laden train going at about 160 kilometers an hour. This is serious, and a huge amount of stored magnetic energy in the magnets. So our machine protection systems have to be very, very reliable. Injection, collimation, beam dump, and RF. And I'll come back to these very briefly just to give you an idea of the key systems. So just again, a schematic just to show you the layout. So injection at points 2 and 8. Atlas and CMS, the big detectors at 1 and 5. Our beam dump over in the woods at point 6. RF at point 4, and collimation at point 7. And you notice for most of the ring, the beams are traveling in separate beam pipes. So the blue on the inside and then switching to the outside, and similarly the red coming in on the outside, going to the inside, switching to the outside. So they both travel the same amount of distance as they go around the 27 kilometers. We've got dipole magnets. So you see the cables wound into coils. You see the cross sections of the coils here. Huge force is generated by the 12,000 amps. So the collar's holding everything in place. This is hundreds of tons per meter, trying to push the coils apart. And these producing a very, very, very pure dipole field in the two apertures, in opposite directions in the two apertures. And then stuck inside a cryostat, keeping it all nicely cold at 1.9 K. So as you saw, 1,232 of these. And this is Lynn Evans, Welsh, former LHC project leader. Superconducting RF cavities. So we're going to pump RF power at 400 megahertz into our cavities and set that at the resonant frequency, and you get an oscillating magnetic and electric fields charged sloshing around on the surfaces of the cavities to produce a longitudinal electric field on the axis of the particle beams. So the bunch is going to arrive here when the field is pointing in the right direction, and be accelerated and bunched by this oscillating electric field. So our acceleration section is only about 30 meters in length, 2 cryo modules, each with 4 cavities per module, providing 16 megavolts of accelerating gradient. And this we use to accelerate the bunch and accelerate the beam. So it takes LHC about 30 minutes to get to top energy, but it's driven more by how fast we can ramp the magnets rather than the RF. This is what actually gives the protons their additional energy. Very good vacuum in the beam pipes. We don't want our high energy protons colliding with the nucleus of gas molecules. So we pump in the superconducting regions, the cold surfaces, pump all gases except helium. We have warm turbomolecular pumps to get things down to a reasonable level before we cool down. And we use a non-evaporable getter, neg, which is like a molecular flypaper, which we coat the warm parts of the machine to give us a very good vacuum of around 10 to the minus 10 millibar. And one challenge, very cold, very dark, relatively 50 millimeter hole. We're threading a proton beam with 400 megajoules through superconducting magnets, where we can afford to lose around 50 to 100 millijoules per cubic centimeter. So this is to stop protons wandering off into the magnets. We have a very sophisticated collimation system. So this is a collimator, a meter long. This is carbon fiber composite jaws, extremely well, very, very precisionally machined flat surfaces. And you see 2 jaws, this is going to be a vertical collimator and the beam going through this. So typical distances I'll show you. So the idea here is if we lose a proton from the circulating beam, it hits a primary collimator, showers onto secondary collimators. The tertiary halo is mopped up by other tertiary collimators and shower absorbers. And we have protection devices also there, defining a hierarchy which allows us to to mop up all the protons that wander too far out. I won't go to any too much detail there, but you get the idea. This is a picture of each one of these is a meter long jaw at different points around the ring, and the white line is the aperture defined, and this is the setting of the collimator in millimeters. So these gaps are around 2-3 millimeters wide. So the proton beam going through here and, as I say, keeping things safe. We test, so 27 kilometers, beam loss monitors, 4,000 of them around the ring. We generate losses and make sure that everything goes where it should do into the collimation sections around the ring, getting this fabulous cleaning efficiency, protecting the cold sections. Right, video. Let's go. We're going to go down in the LHC tunnel for a couple of minutes. I hope this works. Let me know if you don't.
Okay, we're in point 6. And these are the extraction kickers for beam 1, TCD. Is offering protection to the downstream section. Okay, the sector have guided extracted beam 1 up into the upper pipe of the 3. They're finishing the installation of the full complement of dilution kickers.
Okay, I'm going to wander on a little bit further. So there you go, you can see the actual beam pipes actually getting quite big now. Hi.
Okay, we're carrying on down into sector 6-7. You can see the arc bending away. And we're arriving at the point where the beam dump pipe heads off down beam dump tunnel. And I suspect that's going to be as far as we go. It's usually restricted access in that tunnel. We're now looking down the beam dump tunnel. Okay. Limited state radiation area. And if we were to carry on down 700 metres, we come to the beam dump block.
Okay, that was the beam dump. So that was the beam dump of beam 1. There's another one on the other side, similar setup for beam 2. So just the LHC cycle, we inject from the SPS. As you saw, up to 288 bunches at a time. Takes us a long time to get up to about 15 minutes to get the full complement of around 2,500 bunches. 15 minutes to go up to top energy. We reduce the beam size at the interaction point, and then we sit there in stable beams, continually delivering collisions to the 4 LHC experiments for about 10 to 15 hours on a good day, if nothing trips off. And that's the LHC cycle. Dump the beam and then ramp down and go again. Nominal bunch structure, just flash this so you see we see the 72 bunches from the PS. SPS takes 4 of those and sends them off to the LHC, and we take about 12 injections to fill up the LHC, leaving a gap for the beam dump kicker to come up. Okay, 25 nanosecond bunch spacing, and that's the full component that then goes up to high energy. So images of the beam, the transverse images of the beam from synchrotron light emitted by the protons, which is collected into a telescope system, which gives us the beam size for the whole complement. So they blow up, these are the ones that came in first, and you see they've blown up a little bit while sitting there at 450 GeV. We cross the beams at an angle so that we don't get collisions either side of the central interaction point. This just for a few hundred meters, well, 100 meters or so either side of the interaction point, and then we go into 2 beam pipes. So you see the setup. So crossing angle in Atlas, Alice, CMS, and LHCb. So the crossing angle, and then we reduce the beam size at the interaction point to maximize the chances of a collision at the IP. And so you see the crossing angle, and you see the very small beam size, 17 microns sigma here, compared to about 1.5 millimeters in the triplet magnets, in the strong magnets either side of the experiment. So this is the squeeze. And the aim of the game, maximum number of collisions, maximum beam energy, maximum physics reach. And this is encoded in a quantity called luminosity. So we have n particles in beam 1, n particles in beam 2. We try and keep this, maximize this, reduce this as much as possible to ensure the highest collision rate that we can. So for luminosity, I won't go into it, but you can just take collision rate as an avatar for that. Lots of protons per bunch. We pass the bunches through each other at the interaction point. So a lot of protons, but only 30 collide at each bunch crossing. Remarkably small things, so most of them miss each other, come back around 89 microseconds later, the bunches cross again. So 30 collisions per crossing, 11,000 crossings per second, lots of bunches. This is an old plot, 400 million collisions per second. More recently, up the number of protons, and reduced the beam size to give us 1.5 billion collisions per second in Atlas and in CNS. So lots of bunches, lots of protons, small beam size, and it all works out. A beam going around 11,000 times a second gives us a lot of collisions per second. So that was overview of the main components and the operational cycle. Life is not easy. LHC originally conceived in '84. The SSC, which was going to be built in Texas, was cancelled in '93. The LHC was approved in '94. We had a lot of this was no, I won't go into the schedule, but it was late. On September the 10th, 2008, we invited the world's press in for the first circulating beams. That's me there. And then 9 days later, we blew it up. So we had one of these welds here, wasn't done properly, had an arc, released helium into the magnet enclosure, ripped up a few hundred meters of magnets. We were off for over a year picking up the pieces. And this was a withdrawal from the community for meditation and preparation. Came back in 2029, having fixed the problem. First collisions at high energy, well, half energy, March the 30th. And then things got interesting. And 2 years later, discovery of the Higgs. So we were very fortunate. Okay, heroic subplot. This is Iron Man. I'll come back to that later. So it was late. We were over budget. We blew it up after 9 days. Costly, lengthy repair. The Fermilab were getting into the Higgs exclusion game. We had to run at half energy because of the issue with the joints. And yet, so this is the events, photon events coming into Atlas. And they were looking for the decay of the Higgs into photon. And lo and behold, after collecting quite a bit of data, we did well. We had this bump here, which was the Higgs. Just to show it's not smoothing. Electron cloud. So we get electrons emitted from the surface of the beam pipe, accelerated by the beam, get an avalanche process, high heat load to the cryogenic system, and it messes with the beam. Electron cloud. We had UFOs, so bits of stuff falling off the beam pipe, falling through the beam, generating enough beam loss to dump the beam. We had problems with radiation to electronics, so non-rad hard components, something we take very, 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 very seriously now. So test everything before we stick it in the tunnel. We had unidentified lying objects. There was something lying on the bottom of the beam pipe that got in there. There's another example of unidentified lying objects in the control room. This is the electron cloud team doing electron cloud studies, but having a nap while collecting data. Problems. Weasels took out a big and more than one transformer. They get on top, get in the bushings and zap themselves and take out our transformers. Our main power supply blew up in the PS, and vacuum leak in our beam dump in the SPS. Takes a lot to keep things running. Highly committed team, moving heaven and high water when we do get problems. So now, 2024 for the LHC, a record year. So this is integrated luminosity. So if you like the integrated number of collisions, and you see 24 compared with earlier years, and just how we've managed to push the performance through the year. So inverse femtobarn is a remarkably, so this is an inverse femtobarn, is a remarkably small area, 10 to the minus 39 square centimeters. If you multiply this by the cross section of a proton, you get 10 quadrillion messy proton collisions. So around 7.5 million Higgs per experiment in 24. So that's about 1 to 2 Higgs per second. So 1.5 billion collisions, 1.1 to 2 Higgs. And just quickly flash, we not only do protons, we also do lead ions. So they're fully stripped by the time they get to the LHC. And we get some spectacular events in all the experiments. So this is the nucleon-nucleon equivalent on 5.36 TeV per proton or neutron in a lead-lead collision. So isotopically pure, this is modern day alchemy being converted into champagne. And you can see the LHC control room. And you see we practice this quite hard. And okay, very good performance. So what's next for the LHC? Physicists want to study the Higgs in detail, looking for new physics. We've seen that we don't have all the answers. So we're upgrading the LHC to the high luminosity LHC. So we're going to deploy this in 26, 28 and try and collect 10 times more data in the following decade than we did in the previous 15 years. And this is what the experiments are after. We're going to now be delivering 200 proton-proton collisions, so it's now about 60. So higher collision rates and a lot more data. And this is the challenge for the experiments. So it's really crowded in here. So 200 proton-proton collisions per bunch crossing in around 10 centimeters. Major upgrades for Atlas and CNS to deal with this. And they're building the components at the moment. No time to go into any details, but challenging upgrade. And they're late. Just to flash some of the subcomponent work that's going on around the world, really an international effort. Coming to the machine, again, an international effort. This is the LHC tunnel, quadrupoles, dipole, collimators, dipole, crab cavities, new civil engineering structure to hold all the powering equipment, machine protection, cryogenics that feed into the tunnel. And that's just well, just to explain the 3-letter acronyms. So these are new magnets that have been developed to go here. So this is the actual realization of those magnets. This is the setup I showed before in SM18. This is about 2 weeks old. The last magnet went two weeks ago. The last magnet went in there, including superconducting links, so magnesium diboride superconducting cables at 25K, carrying around 120K. And this goes from up here down here to feed into the magnets, and the magnets up here. Civil engineering had to drop into set new caverns to build the galleries, and installation undergoing there. So just going another video to show you some high luminosity LHC highlights. Okay, right. So very briefly, just quick look to the future before I finish. So just to point out colliders, circular electron-positron colliders, hadron proton-ion colliders, or linear electron-positron colliders. So each have their own benefits, and over the years, the community have made very good use of lepton accelerators and hadron colliders. And of course, what we're now looking at is over here to see for what could come after the LHC. So here we're looking to start operations around 2045. So the LHC should be good till 2041 in principle. Okay, at CERN, you can think of doing FCCEE, so a 91-kilometer electron-positron machine, or a linear collider, so warm or superconducting. Proton-proton is a natural continuation of the FCC. I'll flash the plot later just to show a schematic to show you that. So like LEP, electron-positron to the LHC, proton-proton, and muon collider is another option. So that's that's it on the local area. I won't say it's just our top candidate at the moment, the one that CERN's pushing, is the FCC. So you see the present complex, and the FCC would be 91 kilometers circumference, wandering off under Lake Geneva, out around the local limestone mountains, and back round. So the idea here is to, as I say, run it first as an electron-positron machine as a Higgs factory before moving to a proton-proton machine. And you see the dates of operation for those two possibilities. Detailed civil engineering study, including some drillings in high risk zones. So a lot of material coming out, so 6.2 million cubic meters. 12 access shafts and 8 points around the ring. So the feasibility study for this has just been delivered about a week ago after a lot of effort. Not approved yet, and cost is going to be the issue here. Muon collider, another one that's out there. Muons, nice, heavier than electrons, suppresses synchrotron radiation, but the rest lifetime is 2.2 microseconds. So we have to move quickly. We have to produce the muons, capture them, cool them, accelerate them some more, and then collide them. And okay, pions decay, produce protons onto target, produce pions, pions decay into muons, and then we have to move quickly. And if you are fast and you can produce enough muons, you can have a 200 millisecond cycle. So fast cycling machines here, and proton driver, front end cooling, acceleration, and collider rings, with lots of interesting magnet challenges to keep us busy for a couple of decades at least, to meet some of the challenges involved there. But just to flag that, as there's plenty more out there on the web if you want any more details, but just to let you know that's semi-seriously being considered as a more distant option. Okay, we all get together as a European Strategy for Particle Physics in June, open symposium, a community-wide event to debate future orientation of European particle physics. So this is something done every 5-6 years to set the strategy for the next 5 to 6 years. And this is where we hope to make the decision between one of those options I showed you in the previous slide. Okay, closing. Many unanswered questions in fundamental physics. So going back to the start, what is the unknown mass and energy of the universe? Why this unbalance between matter and antimatter? Is there only one Higgs boson? and why is gravity so weak compared to the other forces? So CERN will continue to have lots of fun trying to answer those questions. This should keep us busy till the end of the century if we get the money. And just leaves me to say cheers. And I'll finish there. Thank you very much.
Thank you so much, sir, for the talk. It was actually really, really interesting. We learned a lot from it. Does anybody have any questions they'd like to ask? All right, I don't see anybody. We have one question, sir. Could you elaborate on the specific purpose that the FCC will serve in the future?
So can you repeat the question?
What is the purpose that the FCC is trying to serve in the future?
Yeah, no, very, very good question. So you saw I mentioned briefly the fact that so two versions, electron positron. So this isn't the energy frontier. This is what we call the intensity frontier. So the term used is Higgs factory. So to produce a huge number of Higgs and examine it in exquisite detail. So the Higgs, very strange particle, could be the portal to new physics. So looking for deviations from the expected standard model properties. So really homing in on the Higgs as a kind of way to access new physics. The second phase, the proton-proton, would take us into a completely new energy regime, up towards 100 TeV, center of mass collisions. There's still fervent believers in supersymmetry and high mass options, which could be the dark matter candidates that we're looking for. So new physics, new big unanswered questions out there at the high energy frontier. So precision with the Higgs, and then exploratory with the protons.
Thank you, sir. I have a question as well. You gave us a lot of measurements, right, about the number of collisions, the width of the beam, and all of that. How do you make such precise measurements without, hurting the beam or changing direction that it's moving in and things like that? How do you have precise measurements?
The precise measurements of the
width of the beam and the number of particles that are in the beam and all of that. How do you
yes,
make those measurements without changing direction of the beam or in?
it's a very interesting question, and I'll give you the simple answer. We call this the luminosity. So luminosity times cross section gives you the number of events. This is very important for the experiments who are looking to establish the cross sections of these different processes, like the reduction of the Higgs. This really is a very important prediction by theory, and it's good. So we have to be able to measure the luminosity very carefully. And in fact, one way we do it is we need to measure the number of protons in the beam very accurately. So we have dedicated what we call beam current transformers, which measure the current. So but we also measure the beam size at the interaction point. And this we actually do by sweeping the beams across each other, transversely, vertically and horizontally, and looking at the luminosity variation as you do that. And if typically the beam's Gaussian, so if you sweep two Gaussians across each other, you get another Gaussian. And from that, you can actually deduce the size of the bunches that are crossing. There's bunch-to-bunch variations, and there's all sorts of different effects that have to be taken into account. The experiments turn up regularly, spent a lot of time doing detailed measurements in the control room to get a handle on these numbers. So it's not easy. In answer to your question, it's not easy, but the main way is these what we call luminosity scans.
Thank you so much, sir. Are there any other questions? We have a question. What role does string theory play now after we have all the experiments done at the LHC and all of that? Like, does it change between what information we had in the 90s when it was first proposed versus the information we have now?
Which theory?
String theory.
String theory. Yeah, no, string theory is kind of out at another another energy range completely. Although there are some theories that make predictions that could be accessible, particularly get extra dimensions. But for the moment, nothing. So I think the theory side of things has developed an awful lot. But experimentally, nothing has shown. But that is true of that's true of straightforward supersymmetry, superstrings, extra dimensions. There's a whole swathe of things that the experimental physicists are looking for. No deviations whatsoever from the standard model for the moment. And this is what I've said earlier: the unreasonable effectiveness of the standard model. So I've seen bumps come and go all my career, and it's staying strong for the moment.
Any other questions? Right. So we have a question. What would be ways that we can, like students after we graduate, come and participate at CERN, maybe as an intern, go look there for their opportunities and research and things like that?
No, absolutely. There's quite a wide range of programs, and I think as an associate member state, you are entitled to access these programs. If you go onto the CERN careers website, technical students, graduates, apprentices, so a number of opportunities. I'm really very happy for anyone to take advantage of that if they can.
All right. Anything else before we let him get back to his very busy schedule?
So my question is, how would the FCC be able to access 100 TeV? One obvious advantage is it has a higher radius, so less synchrotron radiation. But what are the other factors?
Yep. Okay. So so 100 TeV. We're talking 50 TeV protons. So 100 TeV is the kind of center of mass energy. So what we need to do, strictly, I talk momentum. It's the same, but the momentum goes with the product of the radius of the ring and the magnetic field, the B field. So LHC 8 Tesla. We'd like to go up to 16 Tesla. So you double the B field, the strength of the B field, and you increase the circumference by a factor of 3. So there you get your factor of 6, which takes you up from 14 TeV to 100 TeV. So this is simply stronger magnets, bigger ring, higher energy. And then of course you're right. You mentioned you have to take care of the synchrotron radiation, but okay, that's manageable.
Okay, thank you, sir.
Good.
Anybody else? All right. We thank you so much for your time, sir. It was a very engaging talk. Really appreciate you coming out. I mean, and spending time to teach us about all of this. We know you have a very busy schedule. So thank you so much for your time.
No, it was a real pleasure. Thank you very much for having me. Okay. All the best.
Thank you.
Bye-bye.